Hello everyone, welcome to today's class. Today's class is going to be about properties of electric field lines. See, the study of properties of electric field lines becomes of paramount importance because this topic leads you into the electrostatics 2 part. And electrostatics 2 part deals with electric flux, Gauss law, and these are the topics that are of vital importance when it comes to your JEE Advanced. In today's class, we are going to deep dive into the various properties of electric field lines. I'm not just going to tell you about the properties in itself, I'm also going to make you understand why these properties are so. I'm going to give you the logic behind it, and after today's class you will be able to explain it to every one of your friends how these properties came to be. See, most of the people will be knowing about the properties, but you will have the added advantage of knowing why these properties are so as they are. Okay, let's start with today's lecture. I'll be starting with a very basic property, something that you've already sort of studied in the electrostatics 1 part. The electric field lines originate from positive charge or infinity. Now, when I ask a student, where do electric field lines originate from? Mostly he tells me, sir, they originate from a positive charge. But here is something extra for you to remember. Electric field lines originate from positive charge or infinity and terminate at negative charge or infinity. Terminate at negative charge or infinity. Now let me make you understand this little thing. Let's say I have a plus charge Q plus Q charge. Okay, now what is how the electric fields are aligned in space of a plus Q charge? We all know they are aligned radially. This is not something new for us. But now you tell me, here we can see that the electric field lines are originating from the plus Q charge, but where are they terminating with respect to this figure? Sir, these tend to be terminating at someone far away. So what is that far away? That is going to be infinity. Now let me take another example of a negative Q charge. Now when I ask you about the negative Q charge and the electric field lines of it, you will say, sir, draw the radial field as you drew for the positive Q charge, but this time what you are going to do is reverse the arrow. Now the electric field lines are going to come towards the plus Q charge. Sorry, the negative Q charge. Okay? Just like this. Now in this figure, where do the electric field lines originate? Sir, they originate from a far away place which we term as infinity, and they terminate at the negative Q charge. So this is simply what the first property of electric field line states. Okay, now copy it. I'm going to erase it and I'm going to start with the next property. Okay, pause and copy. Now what is the next property? See, the first one was fairly simple. So is the next one. See, let's say in space there are two charges, plus Q and plus 2Q. Now if I ask you what is the electric field at point C, let me say that this point over here is C. And if I tell you the distance is from 2Q and Q, let's say this distance from 2Q is R1 and from plus Q is R2. Now I think most of the students are going to tell me very easily that electric field C, sir, is because of Q it will be in this direction, because of 2Q it will be in this direction. But if I ask you, let's say this is E1 and this is E2, let this be charge 1, let this be charge 2. But if I ask you what is the electric field at point C, then most of the students will be aware about this. We will be calculating the net electric field. And how do we calculate the net electric field? So we take the vector sum of E1 and E2. Why? Because electric field is a vector quantity. I must put an arrow over here. Okay. So for net electric field, we are going to take the vector sum of E1 and E2. Now, I'm not concerned about the magnitude bit of it. This you have already studied in the previous lectures. I'm concerned more about the direction. You tell me what is going to be the direction of electric field at point C. Is it going to be E1 or E net or E2? Now most of the students will know this, that it is going to be this vector, the E net vector. Now when I draw electric field in space, electric field lines in space, I take it into consideration that the electric field lines are drawn in space considering the net electric field. They don't take into consideration the E1 bit, the E2 bit, they take into consideration the net electric field. Now let's say this is how the electric field lines are in space. If the electric field lines are like this in space, then this tells us that at every point the electric field is the net electric field due to all the charges present in this region. Okay, I hope you understand this. Okay, it was fairly simple for you to understand, nothing complicated. So what is the second property? Electric field lines represent net electric field in the region. Field in the region. Okay, this was the second property, which was also fairly easy for you to understand. Now I'm going to erase it. You can pause and you can copy it if you want. Okay. Now moving on to the third property. Now I draw electric field lines first. This is how electric field lines in space are. Let's say the electric field lines in space are like this. Now if I need to calculate the direction of electric field at a particular point, let's say a particular point C, someone has asked me to calculate the direction of electric field at point C. Now we know about the electric field lines being in this manner, but if I was asked about the direction of electric field at point C, what I need to do is I just simply need to draw a tangent at point C. Okay, now this is how I drew a tangent. Now the tangent at a particular point on the electric field lines is going to give us the direction of electric field at that point. Okay, you understood it? Let me take another point. Let's say I need to calculate the direction of electric field at this point. Let me name it A. Now what is the direction of electric field at A? How we are going to tell that? We are going to draw a tangent at point A. Once we draw the tangent, that tangent is going to give us the direction of electrostatic field. Now one more thing. What is electrostatic force? Electrostatic force is Q into E. So whatever is going to be the direction of electric field, the same is going to be the direction of electrostatic force. So in this case, in the case of electric field lines, when we draw a tangent at a given point, we get the direction of not only the electric field but also the direction of electrostatic force. Okay, now this is a minute difference with respect to magnetic field lines. I know you have not already studied it, but when I'm going to teach you that, I'm going to tell you once again, but let me tell you here also, when it comes to the magnetic field lines, then when we draw the tangent at a particular point on a magnetic field line, we will only get the direction of magnetic field, not the direction of magnetic force, because magnetic force is Q V cross B. So there the direction of magnetic force is perpendicular to the direction of magnetic field. This I am going to teach you in a great bit of detail in the chapter of magnetism. But this was something that I wanted to put it into your mind so that you be aware about it and it doesn't hurt. Okay. So what is the third property? Tangent at any point on electric field lines gives us the direction of electric field and also electrostatic force. See, this was also fairly simple. See, these properties are going to be simple only. You just have to have your attention span right here. You won't be in any trouble. If you put all your attention over here, these properties are not going to trouble you a bit. Now we are moving on to the next property. This is from where a little bit of fun begins. Okay. Now the next property says that two electric field lines will never intersect each other. Okay. I cannot draw two electric field lines in a manner that they intersect at a point. Now, why is it so? See, I've already told you about a property which gives me the explanation that why this case cannot be possible. Most of the students must have thought about it also, but let me give you an explanation. See, at point A, let me take this as point A, and at point A, if I draw a tangent, now if I ask students to draw me a tangent at point A, some students will say, "Sir, this is my tangent," while some students will say, "Sir, this also is my tangent. This is connect at point A." Now there are two directions of the tangents at point A, and if there are two directions of tangents at a point A, there are two directions of electrostatic field also and electrostatic force also. But we know one thing, in space, let's say there are various charges, several charges, q1, q2, q3, and I ask you about the force that this q4 experiences over here at point C. Now, if I ask you about the force that Q4 experiences, you are going to give me a definite direction. There cannot be two directions in which the Q4 experiences force. So, in this case, when the electric field lines intersect, there are two possible directions of electric field and hence two possible directions of electrostatic force, which is never possible in real case scenarios. Okay, hence two electric field lines never intersect each other because at the point of intersection there are two directions of electrostatic field and two possible directions of electrostatic force, which is not possible in space, as we have seen via this example. If I ask you about the direction of electric field at point C or the electrostatic force experienced by Q4 at C, you are going to give me a definite answer. First, we are going to draw the electrostatic force experienced by Q4 at because of Q1, then because of Q2, then because of Q3. Now the diagram is a bit shabby. Let me draw it again. Okay, this is Q4. What is the force that it experiences because of Q1, because of Q2, because of Q3? Now because of Q1 it experiences some legit force in this direction. Because of Q2 it experiences in this direction, and because of Q3 it experiences in this given direction. But the net electrostatic force is going to be, let's say this is F3, this is F1, this is F2, but the net electrostatic force is going to be the vector sum of F3, F2 and F1. Hence, there is going to be only one direction of electrostatic force experienced by Q4, which is contradicted over here. Hence, two electric field lines can never intersect each other. Okay? Now, this is also a property I think which I have conveyed to you very well, and most of the students would have understood it. Those not paying attention over here, I cannot say about those people, but who were with me throughout this explanation must have found it to be fairly easy. Now moving on. The next property. Electrostatic field lines can never exist in closed loop. Okay. Now this is a closed loop. Why electrostatic field lines can never exist in a closed loop? I need to give you an explanation also. Now there are two explanations to it. One is a very fundamental, rudimentary, childlike explanation which I am going to tell you first, and then there is going to be an explanation which involves a bit of physics, which involves a bit of knowledge about the previous chapter of work per energy. Now let's see how many of you can recall about that chapter. Okay. Now let's say I take a point A. Now, if electric field lines exist in a closed loop, then at point A, they are also originating at point A and also they are terminating at point A. Is that possible? You studied the first property of electric field lines. Electric field lines either originate from a positive charge or infinity or terminate at a negative charge or infinity. But in this case, what do I consider A as? Can I consider A as a positive Q charge? No, I cannot, because see, the electric field lines are originating, that's okay, but they are also terminating over here. So this is the first explanation, and this is a very fairly simple childlike explanation that I gave you here. But because we are studying physics, I'm going to give you a better explanation of this also. Okay, now another loop I have drawn. This is how the electric field lines are in a closed loop. Now tell me, If electric field, or rather if electrostatic force is a conservative force or a non-conservative force. This you have studied in electrostatics 1 part. Is the electrostatic force conservative or non-conservative? Now many of the students must be recalling in their minds what is conservative and what is non-conservative. See, this concept was introduced to you in the chapter work per energy. Conservative force is a force which does not depend upon the path taken, whereas non-conservative force is the force which depends on the path that you take. Okay, now in electrostatics 1, you are told that electrostatic force is a conservative force, and because it is a conservative force, it is a property of a conservative force that work done in a conservative force will always be zero. Okay, now this is a property of conservative force. This you studied in work per energy, that work done in a conservative force field, force field is zero. This was taught to you in the chapter work per energy. Now why it was so, I'm not going to get into much details, because see, the potential energy concept was introduced only for conservative force, and if something exists in a loop, then potential energy at this point is going to be a constant. If I ask you about the potential energy at point A, then it is going to be a definite value. And what is potential energy? Potential energy's difference, potential energy initial minus potential energy final, is work done by conservative force. Now you tell me, if I talk about just this point A, what is the potential energy at A? Potential energy at A. And if I travel a complete loop in a conservative force, then I again reach at A, then potential energy at A is also A. So what is work done by conservative force? It is zero. So because this cancels out, so work done by conservative force comes out to be zero. So I've also given you the explanation that why work done by conservative force in a closed loop is zero. This is the explanation I've given you. Okay. So in a conservative force field, work done by a conservative force in a closed loop is zero. This is the explanation I gave you. Okay. Now tell me, let's see, we take a very small ds bit of this circle. Now tell me, what is the direction of electrostatic force in this ds part? You say draw a tangent. This is the direction of electrostatic force. Now what is the direction of displacement for this small segment? What is the direction of displacement? It is also perpendicular. These both are parallel to each other. So this is the direction of ds. What is work done? Work done is integration of f dot ds. And what is the angle between f and ds here? It is going to be 0, and cos 0 is 1. See, dot product. Once I open the dot product, this will come out to be f ds cos 0, and cos 0 is 1. So I can just erase it and say this is 1. Now if I do this complete integration, will it come out to be 0? Will it? No, it will come out to be a definite value. Let's say it will come out to be a definite value. Okay. Now, but what was the property of electrostatic force? That work done by electrostatic force in a closed loop has to be 0, because electrostatic force is a conservative force. Hence, by this explanation, because when we consider electric field lines to be in a closed loop, the work done is coming out to be a finite value, which is not possible. The work done by a conservative force in a closed loop has to be 0. Hence, electric field lines cannot exist in a closed loop. Okay, so there were two explanations of it. First explanation was the simple one, that if it originates from plus q, it cannot enter into plus q. And the second one was where physics was involved. The prior knowledge of your chapters was involved. Okay, now let me move on to the sixth property. Now this fifth property is where I have not written it on board. You can write it. I am dictating it to you. The fifth property states that electric field lines can never exist in a closed loop. And there are two reasons behind it. First, you already know. The second reason is work done by conservative force in a closed loop is 0. But we found that when electric field lines were existing in a closed loop, the work done doesn't come out to be 0. See, we calculated that. Hence, they cannot exist in a closed loop. Okay. Carrying on to the sixth property. Now, I have drawn electric field lines in space like this. And I take 2 points here. This is point A and this is point C. Now, the property states that the electric field intensity is directly proportional to the electric field line's density. See, this is the property. Electric field density is directly proportional to the electric field intensity. Now, this is also something that you were aware about. See, if I say, first, consider the property, look at this figure. If I ask you at point A and point C, what is going to be the relation of electric field at A and electric field at C? You are going to use this property and you are going to tell me, sir, electric field at A is greater than electric field at C, and which is also true. Okay? And here, okay, so this is fairly simple. And here we studied that electric field density. See, here the fields are dense, here they are less dense, here the electric field lines are more dense. So electric field intensity is also going to be more over here. This is what the property says. And this is something you can copy it. This is something that you've already done in previous classes. I'm just stating over here, but this is something that you've already done. When we drew the electric field lines because of a plus Q charge, let's say this is a plus Q charge. See, this is how we drew the electric field lines. Okay, and we know as we move away from a plus Q charge, the electric field intensity decreases. Do we know about it or we do not? All of us know that E is inversely proportional to R square. Oh, or E is directly proportional to 1 by R square. So as we move away from plus Q charge, the electric field intensity decreases. Now if I talk about the density, see, density will be more over at this sphere A or at this sphere B. Number of electric field lines passing through A will be equal to the number of electric field lines passing through B. This everybody can understand. This is fairly simple also. See, this is a sphere. So this is enclosed plus Q charge. So the number of electric field lines that will be originating from plus Q will be crossing from the sphere A also. And the same number of electric field lines are going to be crossing from the sphere B also. But what is density? Density over here will be the number of electric field lines which will be crossing the sphere, and the electric field lines will be crossing at the surface of the sphere. So we can roughly say density will depend upon the area here. Otherwise, density is mass upon volume. I'm not talking about that density. I'm talking about how many electric field lines per unit area will give us the knowledge about the density of electric field lines at a surface, because I'm talking about the surface here. See, here I've got a plus Q charge, here I've got a sphere A, and here I've got a sphere B. Now when electric field lines emanate from plus Q charge, they cross both A and B, and when they cross A, if I look at the surface area of A, it is smaller, the surface area of B is larger, and because the surface area of B is larger, when let's say we are on the surface of B, we'll see that electric field lines are farther away and electric field lines at A will be closer to each other. Hence, the density at A will be greater than density of electric field lines at B. I hope I am making my point clear that electric field density is directly proportional to electric field intensity. Okay, see, density is more at A, less at B, and hence the intensity we already know, as we move away from plus Q charge, the intensity decreases. Okay, what is intensity? It is the magnitude only. Okay, don't get confused with the new term intensity. It is us or me talking about the magnitude bit of it only. Okay, now this is the penultimate property that we have studied. Now moving on to the last property. Now let's say I have a charge plus Q. And I say the number of electric field lines originating from this plus Q charge is 1 lakh. Let's say this is the data that is given to us. And in turn, I have been asked this question that there is another charge plus 2Q. How many electric field lines are going to originate from plus 2Q? Currently, can you answer me this? I think most of the students can, but let's say some of you don't have an idea about it. So we can say that because of it is a property of electric field line that if 1 lakh lines originate from plus Q, then 2 lakh lines are going to originate from 2Q. Why? The number of electric field lines originating or terminating is directly proportional to the magnitude of charge. This is fairly simple for you to understand also, magnitude of charge. And this is very simple for you to understand. What was the formula of electric field? Electric field formula is KQ upon R square. Now we can also see that the magnitude bit is directly proportional to Q, and more the magnitude, more, see, intensity and magnitude is the same thing. Intensity, magnitude, these are synonymous to each other when I say about it. So the intensity, the magnitude of electric field is directly proportional to Q. Hence, the intensity is directly proportional to Q. And we saw in the last property that the intensity was directly proportional to density also. And that gave us the idea about the number of electric field lines. And hence, this property came into origination. See, all these are interrelated only. We are just studying it in isolation to understand it well. Okay. Now, what does this property say? That the number of electric field lines originating from plus Q, if that is given to us as 1 lakh, then from plus 2Q charge, the number of fields originating will be, electric field lines originating will be 2 lakhs. It is simple. Okay. And this is the statement. Number of electric field lines originating or terminating is directly proportional to the magnitude of charge. Now, this was all the knowledge you needed about the properties of electric field lines. Now we'll move on and we'll do, see, not a lot is left in this chapter, in this topic rather. I just have to make you do a couple of questions. There was one question, it was a very interesting question which was asked in JEE Advanced. But it is a very old question. Back then it was not called JEE Advanced. When I gave IIT JEE in 2012, then there was no JEE Mains in JEE Advanced. Mine was the last batch in which IIT's paper was conducted separately, and there was another paper to get into NIT, which was of AIEEE. But for you guys, there is mains in advance. But this question came way before. Then there was only IIT's paper. So it was given that the diagram of electric field lines was given between 2 points A and B. And it was like this. Okay. It was not symmetric. This curve was not symmetric. It was a little bit bent towards B. Okay. The upper curve and the lower curve was symmetric, but it wasn't symmetric in the plane. Okay. This was the question. This was the figure given to us about the electric field lines. This is A. From A, they were emanating and they were terminating at B. Now, two questions were asked. QA is positive or negative? And similarly, the QB thing was also asked. Is it positive or negative? Now, I don't think there is going to be a kid in this lecture who is not going to answer me this. This is a fairly simple question. Sir, QA is going to be positive only. No, lines are emanating from it and lines emanate from a plus Q charge. So this is going to be the right answer. And B is going to be the negative charge one. Why? They are terminating at B. So this was the easy bit. Okay, you must have secured 1 mark because of this knowledge. But the next question was, regarding the magnitude of A and B. Which magnitude was more, the magnitude of A or magnitude of B? What is going to be the relation between the two? Now, if a student starts counting electric field lines, more electric field lines are originating at A and less are originating at B. Okay, 1, 2, 3, 4, 5, 6. 6 lines are originating at A and at B only 4 are terminating. And I told you number of field lines originating or terminating is directly proportional to charge. So by that property, I can say that the magnitude of QA is going to be larger than magnitude of QB. Okay,